My name is Manuel Hernandez, and on behalf of my co-authors, Yanghu Alka Bishnoi, Rashni Kaur, and Richard Sowers, I would like to thank you for attending our presentation, focused on the exploration of machine learning to identify community-dwelling older adults with balance dysfunction using short-duration accelerometer data. Balance dysfunction is one of the most common fall risk factors in older adults. Instrumented tests focused on balance dysfunction may provide an opportunity for early fall identification in community-dwelling older adults. The motor control test provides a quantitative measurement that is a sensitive indicator for the decline of postural control in community-dwelling older adults. Traditionally, subjective balance tests have also been used to predict balance dysfunction as well as fall risk. However, these tests take time and clinical professionals to administer the tests, also with a higher economic cost. Our specific aims are to validate the feasibility of wearable sensors to identify older adults who have trouble with balance, to explore the possibility of using machine learning algorithms on small accelerometer datasets to identify older adults with balance dysfunction while walking, as well as explore lower extremity sensor locations for accelerometer sensor locations. We recruited the following participants. 21 community-dwelling adults were then divided into two balance ability groups. 12 individuals were placed in a high balance group. They were about 67 years of age on average and had a modified telephony interview for cognitive status, or TICS, of around 25 and a motor control test score of 131 milliseconds. There were also 9 individuals who were placed in a low balance group who were, on average, 66 years of age, had a TICS of 26 and an MCT score of 152 milliseconds. The MCT, or motor control test cutoff latency, was 143.4 milliseconds to separate between the two groups. We placed 2 accelerometer sensors on the right hip and knee. We collected 120 seconds comfortable pace walking with predefined self-selected speeds performed on the treadmill, and 2 independent walking trials were collected from each subject. For data analysis, we then took the acceleration data and truncated it to 60-second independent segments for feature extraction. So on the right, we could see the segment of data where the individual was walking with a comfortable speed. This could then be parsed out into 2 independent segments, segment 1 and segment 2. For statistical analysis, we examined acceleration features for cohort differences using a t-test, where a p-value of 0.05 was set for significance. For data processing and also feature extraction, we followed the following steps. First, data was collected in the hip and the knee at 148.1 Hz. We then applied a high-pass filter of 0.1 Hz and a low-pass filter of 10 Hz to remove both drift and also high-frequency noise. We then went through and identified walking periods and truncated the data into the 2 independent segments, and then carried out feature extraction. The features extracted from the acceleration data include the mean, standard deviation, the coefficient of variance, root mean square, autocorrelation, mean amplitude deviation, signal magnitude area, signal energy, paired correlation coefficient, peak-to-peak mean, peak-to-peak standard deviation, and the peak-to-peak maximum. Both the high balance and low balance group had very similar acceleration frequency profiles. If we take a look at all subjects and break them down into the high balance and low balance group, we could see that the only factor that was found to be significant was the motor control test, which was used for the creation of the 2 groups. But the acceleration data on the hip and the knee in both the XYZ did not show any significant differences between the 2 cohort groups. As can be seen, this is true even though there were different patterns that could be observed between X, Y, and Z between the 2 different groups. There were subtle changes in acceleration-derived features that we found in the low balance group. We found no pattern distinguishing subjects with low or high balance function was evident in the exploratory plots. And no statistically significant differences between subject groups in all features were found from independent tests. For machine learning models, explorations, and results, we first normalized all features between 0 and 1, and then a total of 7 machine learning algorithms were then compared. The decision tree, ensemble random forest, support vector machines with linear and radial basis functions, kernels, gradient boosting machine, adaptive boosting or AdaBoost, and extreme gradient boosting or XGBoost. As we could see, we found that GBM and also the RBF-SVM algorithm showed consistent low false positive rates and high true positive rates, leading to excellent area under the receiver operating characteristic curve. Continuing on our exploration of machine learning models and results, we see that the GBM algorithm achieved the highest levels of accuracy, F1 scores, and AUCs, and the RBF SVM is closely behind, while it was able to achieve a similar level of accuracy. Thus, overall, the GBM algorithm provided the best average cross-validation performance, followed by the RBF SVM by a slight margin. The results of the study suggest that accelerometer data can be used to classify balance dysfunction within community-dwelling adults, which demonstrated consistency with similar ML studies that predicted fall risk in the past. GBM provided improvements in overall classification performance in classifying balance dysfunction compared to random forest algorithm, which was used in past ML approaches to predict fall risk. And in comparison to prior one-sensor systems, the two-sensor approach provides a potential opportunity for the tracking of additional lower extremity motion. Compared to traditional instrumented balance tests, acceleration-based machine learning techniques can be used by a non-clinical professional in any setting, which relieves the time and economic burden on both patient and clinical professionals. In conclusion, in this study, we established the feasibility of using 60 seconds of accelerometer data from wearable sensors when walking to identify other adults who have low or high balance function. GBM algorithms show promise for the use of wearable sensor data to classify older women with low versus high balance function. And our next steps will be to explore the optimal trial duration and data features to best classify balance dysfunction, investigate the optimal sensor location by comparing the corresponding sensitivity of sensor locations in the lower extremity with other commonly used locations, such as the shoulder, and to design a novel classification architecture that is best suited for this task. I would like to thank all of the subjects who participated in the study, as well as Ms. Yanqing Liu, Nicole Shou, and members of the Mobility and Fall Prevention Lab for their contributions to the study, and the Campus Research Board for financial support of this work. Thank you very much.